Good afternoon, everybody. Welcome to our next session here. And we have Łukasz Langa, who's going to be looking at audio.
All right.
Big hand.
Hello. Welcome to PyCon US. Welcome to Looking at Audio, a visual aid in understanding sound. My name is Łukasz. I come from the internet. In fact, it's Poland, but it's far enough, it doesn't matter for you. This is the second year in Pittsburgh, and this year, it turns out it coincides with presidential elections in Poland. So I voted just this morning for my own president in Poland, which I could do before people could actually vote in Poland, which I found hilarious. So that was part of why I actually went through the trouble. But the other reason I wanted to do it was to give me this very smooth segue to criticize your president. Regardless of your views, whether they're conservative or liberal, I don't think you want to have a king, but that seems to be what you'll be having. So I think you should resist. We were lucky enough in Python to have a benevolent dictator for life, and he ended up not being for life. But you might end up with one that is not benevolent. So, kind of resist. But now let's talk about something fun. I have a podcast where I'm also annoying, like now, with a physicist friend, and also did already a bunch of talks about Python on conferences in the past. And a few of them are non-required viewing for you. For other things, I did already with sound. So back in the COVID years, I made a talk about sequencing sound with async I/O using MIDI. Later on, I made a FM synthesizer that does actual real-time audio with Python. Turns out computers are fast enough so that even Python can do it now. But if you help it with Python, that works even better. And last year, I programmed music live using PyRepl at EuroPython. So there's a bunch of things that I did with sound. But now I wanted to talk about what sound actually is and why this is such a fascinating topic for me in particular. So today, we're going to be talking about what this means, what that means, about this and that. Actually, yes, about this. And that's it. So what is sound, right? Sound is this, mechanical wave that makes it different from electromagnetic waves in that it needs a medium to travel through. It propagates through a medium. And since we are talking about human perceivable sound, that medium is going to be air. But that means you're going to have to move the air molecules for anything to happen. So to actually produce sound, we can use something like this simplified form of a speaker, right? Where you pump air by just changing the electric current of the coil. And that makes it move closer or further away from the central magnet, right? And that pushes the air in front, and boom, you have sound. So let's imagine that this grid of dots is air at some particular pressure. So larger pressure is going to be a larger dot, and smaller pressure a smaller dot. So the red dot right there is our sound source. And a single pulse will increase air pressure, and let's see how it propagates. Right, so it propagated nicely. It looks sort of like a wave, with the interesting thing that, when the pressure is higher at one point, it needs to be compensatedly smaller right behind that disturbance. But a single disturbance isn't really a wave yet, right? It was just a pulse. So to actually talk about sound, we need to have, waves of it, so more of that. So let's have more. This was some random phrase, what the tempo in that was. We don't know. And the reason why we don't know was that it was really irregular. Even if it reminded you of something, we couldn't really talk about tempo yet. That's some phrase that we can maybe repeat, but it's really not extremely musical yet. But if you are inputting some regularity into your pulses, then it becomes pretty musical. So if we're doing something like this, regular cyclic pulses, those those are beats. And those are 60 hertz, 1 hertz, so 1 pulse every second, 60 beats per minute, 60 BPM. Relatively slow for music, right? So we can now start talking about frequency, and in musical terms, we are arriving at tempo. So that's pretty cool. And before we get to other things in sound, let me talk to you just a little bit about how this visualization that you just saw was made. So that was made with PyScript. You don't have to write any code down here. You don't even have to understand all of it, because all of it lives on pyscript.com/@AMBV. You can just see all of it. It is out there online for you to consult and run later on. So there's a few examples that I have in this audio-visual collection here, and we're going to start with the sound propagation one. So here you see the pyscript.com editor, where we have like the main file with Python and the result of what we're doing here. So if I press space, we can, in fact, like create some sound. This is done with 3JS, which means like this is actually three-dimensional, so like I can do like weird things to it, which, you know, it would be sort of weird for our visualization, but it's possible because it's a 3D scene. A 3D scene in 3JS, which is something that is a JavaScript library, but thanks to being Python in a browser with PyScript and PyOdide, we can interact with existing JavaScript libraries. 3JS allows us to create 3D scenes. So scenes are those sorts of like tiny universes of objects that are lit by something and looked at by us and interacted with. So a scene is going to have a bunch of objects. Then there's going to be a camera that is like this sort of telescope to our tiny universe where we can actually see a little bit of it. There are kinds of those cameras, like we are using an orthographic one. So like if you ever played any isometric RPGs or real-time strategy games, like that's the sort of view. Like the two parallel lines will never meet at the horizon in an orthographic camera. So that's that. And then we render. What does that mean for us? We are rendering into a canvas element in HTML5. We need some lighting. This light is actually sort of a cheating light, because ambient light just means it lights everything from all directions at the same like lightness level, illumination level, which means those sorts of those spheres don't really look like spheres because they're lit exactly the same. But for our visualization purpose this time, that is actually perfect. So we're using that. Then we're listening to audio. So every time you actually have audio emitted, like we can put it somewhere in our scene. So in fact, this is positional audio here. So it's going to be hard for you to hear it here in the room. But like if we got really far from this particular scene, like by zooming out, like it is going to sound different than it sounds when I'm closer to the source, right? So all of this is a fantastic tool that you can use like for your own sort of like, I don't know, visualization purposes. And I highly recommend you to play with that because it is very rewarding. I love that thing. So then we finally go to like draw our grid of spheres, and objects in 3JS are consisting of like 3 parts. There's going to be a geometry that says like, what are the vertices? What's the shape of the thing? Then you assign some material to it, which means it's going to have some reaction to light that is shining on it, and we combine it into a mesh that you can position. So a single mesh can have a reusable material and a reusable geometry, so you don't have to actually create new geometries like I am here naively, but you know, this is a tiny single file example. Then I have those orbit controls, which sort of let me cheat without any math, so that when I am dragging here, like things happen in a predictable way for me, like, and I can comfortably control what is happening inside the application. And finally, on the space, we are adding 2 waves. I don't actually want to talk too much about this particular piece of code here that makes the waves propagate. Let me just say that like it is trigonometry. Like there's no magic happening here. Like we're doing simply this mathematics straight in Python, straight here inside the browser. So like if you drew it in any other way, in any other framework for Python, like you would use the same formulas for us. And finally, we just have like, you know, this animation loop that we set so that like the actual browser controls how fast the frame rate goes for your particular web browser and display. We're going to see some more things about how fast the frame rates can be in future examples. So that's essentially it, right? That's our example. That's how I made it. Let's get back to talking about sound. So we were talking about beats and tempo. They were really slow, right? Like 1 hertz, 60 beats per minute. And when movements of the membrane are sudden, like the demonstrated thing, like that creates pops, which is why like the sound that you heard, like, you know, was not really extremely pleasant, but that was because we had pops. So we can visualize this by, you know, position of the speaker membrane, you know, literally in space. Time goes right. So there's two details here I should mention. Usually we don't measure audio from the resting point to some extreme, but actually around the extreme. Because like the equilibrium is going to be in the middle, and then the extremes go around this resting point. And in audio, we can just assume that this upper one is +1, this lower one is -1, and you'll be delighted to know that this is exactly what WAV files store if those are 32-bit floating point WAV files. A series of numbers between -1 and +1. They represent the amplitude of the signal. So literally, bigger line, louder sound, smaller line, smaller sound. And you know what? Like, I have a physicist friend, so I am actually obligated to tell you that like sudden changes from like top to bottom there like will not look like this in nature. They will look something more like this, since we are talking about like physical membrane moving. And this actually makes a difference between like projecting sound just like digitally and transforming it, and recording things that happen in real places and like in physical spaces. So usually we will actually call all of what is happening here some oscillation. Like we will store all of this data in memory or in WAV files, and this doesn't really tell us like how quick all of those like samples that we have here, or those numbers, like should be projected onto the speaker, how fast they should play. Usually these days, because of video, we do this 48,000 times per second. So the sample rate for us, how fast should we project this onto the output, is 48 kilohertz right now. 44.1 used to be like very popular with CD audio. Now 48 is what like YouTube makes people actually use. And like there's more physical funny details about how this audio works. For example, in real life, if you have samples that are like those moments in time, you don't actually connect them with like using a line. Like you have to use some nice smooth curve, because that's how real audio works, where you have those 2 points that are like on the top close to this +1. You can see that the curve actually goes outside of this headroom that we had, and this is called the true peak. And this is actually a behavior that is true even in fully digital audio. This is when you're playing something on a speaker, this will happen. So when somebody tells you that analog is better than digital because digital has those staircase, you know, changes because of sample rates, they don't know what they're talking about. So we covered the first dotty version of you know, our amplitude graphs, but that's not really how you look at sound. If you have 48,000 of those things like just being emitted within a second, you're looking more at something like this, right? Like everybody knows the song, right? Like this is like very clear what that is, right? Right, so remember, usually when you work with audio files, like this is how you look at them. And there are things that you can actually figure here out. Like, you know, the top graph is the left speaker, the bottom graph is the right speaker, and you can see the drums. You can see the drum roll, right? You know, right? Like you can see that happening on the left side here. So that's how you usually look at this. And I made this sort of visualization of a WAV file also with PyScript. So let's look at more PyScript. That's why you're here, right? So I have this visualization here looks sort of weird. There's no visualization because you can choose the file that you want. So let's choose it. Actually, let's close the editor for now so you can see more of this nice graph. And we had our never gonna give you up right here. Just a short fragment of it, but like you can see that it's there. And you know, thanks to the PyScript magic, I can zoom in, I can pan, right? Like, you know, left and right. It works better if I'm actually zoomed in. Yeah, so you can do stuff to this audio. Like, and thanks to like a bunch of things that I did, like, you know, you can actually reload the file and choose another one. I know, a very advanced feature, but like now it actually works, so I'm happy about that. There's gonna be another file that like we're gonna see later in the talk. Like, look at this. That looks very weird. And you know why? That looks weird because the browser is like actually reacting to the sample rate that you can set that you have set up within your like audio interface. So in our case, if I just say sound and I go here, will this show up in the right screen? No. Like you'll see that like I have those like external speakers chosen. I cannot actually open this window. Doesn't matter. But like depending on whether I chose the same sample rate that the file is, it's going to have this hair here or not. In this case, I should have actually checked so that it looked clean for you. But it's a great opportunity for me to actually show that like the browser abstracts many things away for you, but sometimes does surprising things. So the waveform that I'm showing here is this perfect thing that you saw before, but it's not perfect here because it doesn't resampling in real time because of web APIs. Okay, so let's look at how this is made. And here, like, I kind of moved to big boy programming because before, like, we just had a bunch of global variables and we called it a day. Like, that's how we should start because Python is for scripting. You shouldn't be ashamed for using fewer lines than more lines. But if you're going to be doing something more advanced, like, you should be using data classes or adders or whatever allows you to actually have, like, this sort of, like, nicer structure. So in this case, it's nice for us to encapsulate a scene and a render and a camera so that you can exchange them as needed inside one application. So for example, you can have an options menu in your game, but also just project the actual, I don't know, terrain, and then have a map, which is going to be a different scene. So that's how you can make many scenes happen in one application. Just abstract it away so that you can start one scene and stop it as needed. Here, like, we actually, you know, add our renderer to the canvas element in HTML when this thing is active and remove it when it's stopping, and so on and so on. I'm not going to go in great detail here, but like all you need to know is that this allows us to just pretend like this is already handled. We don't need to do it for every script later on. And we can focus on business logic. And our business logic is this waveform visualization. We get those two waveforms here, which are just lists of floats, directly from the file change event. So that's a browser event. And in this browser event, we need to decode audio data from the file we read. We just assume it's stereo because that's my rules on this talk. You know, and we just pass it to this data class and instantiate it. And we can start it right there. So that's how we already see that this is sort of like IO-free. Like this class already just deals with ready-made bytes that it can read from left to right. And then it can convert them from this wave information into vertices, so into line segments. This is sort of like a I don't know, like verbose thing that you can do, that you have to do in 3JS to actually make lines work, because lines are actually hard in 3D. They're hard because, unlike any other object, you don't want them to decrease in size with distance, right? Like the actual line trigonometry for 3D spaces is sort of complicated. And here we also interact with JavaScript, which makes us for like actually use those weird like float 32 conversions here and there. But in the end, everything almost looks fine and very easy, except for this weird create proxy that I have to do here, which is there's a bunch of methods that I want to pass as event listeners for the browser. What is happening there is you should call me back when, for example, the user uses the mouse wheel. However, that callback is going to be called a long time in the future. And in Pyodide, that callback would already be destroyed so that we don't leak memory. And that's not good. So to make sure that this doesn't happen, we have to wrap our method in create proxy. And I do it here and not here when I'm adding the event listeners, such that the objects are exactly the same when I'm removing the listener, so that JavaScript also knows what is happening. But the else is pretty easy, like when there is on-wheel events, like we are just moving the zoom factor and the panning like for the graph. That's how this visualization was made. Now we're going to move to, I hope, things that are more impressive, because we're done with this. And it only took us one recurl, so good. Let's talk about that. This is signal that repeats, right? So we say it oscillates. When you zoom out the same signal, it might not be as easy to notice that this oscillation occurs, because now it's essentially just like from the back, it just might look like a single color on the top and a single color on the bottom. Like for this case, if you are dealing with real-time audio and you want to see a single oscillation, there are things called oscilloscopes that will show you a relatively stable graph for just one oscillation. This is extremely useful for tuning and to actually figuring out whether your synthesis is doing a correct thing, especially in presence of modulation. We're not going to be going much into that here today, but that's what it does. It just makes sure that you're seeing a single cycle. Sometimes those cycles are actually double or half of what you would expect, but most of the time they're great. In particular, this Korg NTS2 very well designed for synthesizer use. So I like the thing. So look at us go. We're halfway there. Speaking of this example, there is a 2-to-3 frequency ratio here, right? So you can see that the tempo rate of the thing above is 2, and the tempo rate below is 3. That means for every 2 changes above, you have 3 changes below. And this is sort of a very popular rhythm. In music school, you just actually learn to do this yourself, to play this with both hands. It sounds something like this. Yeah, so when I was in music school, you literally learn to because it kind of helps with hand independence and so on and so on. Yeah, now it's a party trick that nobody's impressed by, Right, so let's make a sound that does this, but the frequency of those oscillations accelerates in time. It still manages to keep that ratio of 2-to-3, but it gets faster as it's going. So let's hear how that works. For a bit, we're going to just repeat the pattern so that you know this is actually what is happening. Now we're getting faster. So you don't look very impressed, but when I first learned about this, it was mind-blowing to me that only by raising frequency, we move from beats and tempo into pitch and harmony. And in fact, the harmony you heard at the end is the so-called perfect fifth interval. It is like a consonant in music. It is very desirable to have. It resolves nicely, this peaceful, people like to hear it somehow, right? So the fact that we can see this 2-to-3 frequency ratio regardless of whether the frequency is super slow and that's a beat for us or it's pitch to us, that's only in the human. In the nature around us, those things are the same, only the harmony one is beating faster than what we perceive as rhythm. So, I mean, you can see that those things are indeed accelerating, right? And this one actually has the correct sample rate, so there's no hair. But you cannot really see the frequencies here. Kind of how do you measure how high the note is at a particular moment. So we have a tool for that, and it's called the spectrogram. This one is not actually done in PyScript, like I just did that in NumPy, like it is on another GitHub repo of mine, but it is this graph that shows us frequency over time. So still, time goes right. And you can see that like white means loud, blue means like increasingly quieter, and black is like minus 120 dB, which is this magical kind of boundary where neither humans can really hear anything anymore, and consumer-grade audio equipment cannot even emit like signal consistently at that level. So black, silence, right? So we have all of this, and you can see that at the end, because that's the signal that I just showed, at the end the beats turn into frequency. But you would expect that there should be those two notes that we've heard, but there's more here, right? There are the two on the very bottom, but then they're repeated, repeated, repeated. And this is only the left channel, so that's only our C note. How come are the frequencies repeated? Those higher ones are called higher harmonics, because that's how the kind of square wave signal actually works in audio. So just for completion, the right one that we're seeing here, that will be our G note, the other component of the interval that we've heard. So that's also having overtones. And this is actually the thing that makes us differentiate between hearing a violin or a saxophone, or like a string being plucked or a string being hit by a piano hammer inside a grand piano. So timbre is essentially higher harmonics and how they change over time. So overlaying left and right channels, you can see that tan taradam in the middle, like nicely obscured by PowerPoint, good job. And on the right, we can see the C and G frequencies over here, right? So like that's the base frequency, and the higher ones are harmonics. Not all waves, like the square wave, are gonna have higher harmonics. Like the mighty sine wave, that is essentially basis for everything in nature, it seems, like does not. So if you do the same exercise, I will just spare you the audible example here, you will only see those two base frequencies. There's not gonna be any harmonics there. Like the people in the back might not even see that there are indeed like just two frequencies there. So that's the sign. And in fact, the way spectrograms work is by this genius invention of a Fourier transform. Like, and this, I also have a mathematician friend, so I'm not going to make a fool of myself and explain too much here. But like, all you have to know is like, this is this sort of like tool where it assumes that a signal, including my voice right now to you, is composed of very, very many sines, right? Of different frequencies. Like, they might be very loud or very quiet at a given moment in time, but it's all sines. So the e to the power of minus j omega t there is just a probe for a particular frequency. And when you have like a sum over all of the frequencies, that's your like spectrum analysis for a moment in time. And then if you go through time, that's your spectrogram. So boom, we're done with spectrograms. But you're like, disappointing. What is this face about? Why is there a face in a spectrogram for audio? Time for some PyScript. So let's go. Where are my examples here? What did I do? Now I'm still switching through slides, but I wanted to switch through my super screens here. No, what is all this? Oh, I have Google Chrome. I want this. Oh, that's what I wanted to be. Cool, so we are choosing files again. And by the way, you're thinking, where do we send those files? Nowhere, to the browser. There is no server here. Like, all of the things that we're seeing with me choosing files and computation happening is all happening on the front end. There is no server. Everything is local here. So we choose a file. Let's just call this specially prepared Python file, which is, as you could probably expect, just a Python logo, right? And thanks to the magic of worker threads, we can actually schedule a worker that will do our computation, and then we can save the WAV file back somewhere to the drive. So we can save it like output 1 here, and it's saved to the same directory. The thing that I wanted to show you before we're actually going to look at this audio, how do I make this disappear? I'm playing. I am clicking somewhere else. this doesn't like it. And it doesn't like that either. Anyway, that doesn't matter. It doesn't obscure anything important. What is obscured here is like, look at this thing. This is NumPy, and this is SciPy. And we're using it in the browser. I find that is pretty cool. With Pyodide, you can do that. So we can actually like use SciPy to read our no, we are actually using what here. Pill to read our image, and then to create a WAV file, we're using SciPy. And NumPy, in the meantime, like in the middle, is for our efficient like buffer storage that we can pass between our threads. So this conversion converts essentially this information that is visual into information that is audible. The worker here that I could spend more time on, but I'm not really doing that good on time, like happens essentially here. And as you can see, the worker script that we are just starting a worker just to execute this one task, it is literally a script that has like no like functions, no classes. That's the task that we're sending to it, which is why all of this behavior here is just on a module level, because it's not really a module. This is really the behavior that we want here. Okay, so enough talking, like let's see how that thing looks like now. So that's one of my favorite audio editors. We can open a thing in it, and there's output 1, proof, like, well, I tested it in the morning, right? But like now, 1359, that's like 159 for you Americans, like open, and we see a Python logo like in a spectrogram, which like is a cool party trick too, because if you actually wanted to listen to it, that's how Python sounds like. Not extremely musical, but Aphex Twin actually released music like this because people will still buy it, and they did. But like, yeah, that's our Python logo in audio form. So okay, let's move on and talk about like this spectrogram, like in just a moment in time, is looking more like this, right? So that's like our square wave, that are all the higher harmonics that you can see. And if you looked at a sine wave, that doesn't have any harmonics. But you're like, Łukasz, I can see some harmonics there. That's because nobody actually uses like the Fourier transform that I showed before. That was for continuous signal. What you have to use is discrete Fourier transforms, but those are super expensive to compute. So instead, you're using a fast Fourier transform, and those are like already like in the realm of approximating what you would get otherwise. So there is some like residual, I don't know, error because of the windowing functions and so on, but that is at minus 110 dB, which, as I told you, is like close to like even, you know, emittable level of audio by consumer grade audio applications, so it doesn't really matter. So we're done with this. And now, the last part is actually not that different. Because this really is what we've seen before as this momentary spectrogram, only in those applications in your car, like from the 90s, or in your stereo system, again, from the 90s. Like those weren't actually using FFT, since DSP wasn't really that powerful at the time. They were using simple band pass filters. So usually they would only have a few of those bands that you see here. This one, 31 bands, like that must have been really expensive, again, in the 90s. Currently, like we are like able to do like extremely detailed frequency analysis even in real time. So time for some PyScript. So now the next example that I have here already has a file loaded in, so we don't play the game again. And there is a blue line that you have here. This line will change color depending on how much signal is in a given frequency, since again, like here, like frequencies go right. Lower frequencies are on the left, higher frequencies are on the right. So the colors are going to be different, and obviously the bars are going to be higher when the sound at this frequency is louder. So there's really not much code that like bears a kind of detailed explanation here. Again, we're using the line segments geometries just so that like the lines can be projected properly on the canvas element. And as you can see here, like we're doing 60 frames per second. Well, we could do like 120 on this screen because the browser actually adapts how fast it's asking you for the animate function based on what you are projecting to. If your animate function is really slow because it's doing very many things, like, well, you're not going to get 60 FPS. But if your animate function is like very short, like it's very quick, you are still not going to get 500 FPS because it does adapt the projection to the display that you're looking at. So in this case, this HDMI cable actually wants me to emit 60 FPS. So that's what we're getting. And now when we're listening to it, you can see percussion, usually high frequencies. Drums, like bass drums, basses, low frequencies. And again, this is 3JS, so like you can do silly things to it, like it's not that it makes much sense. Right, but you can do stuff with that. So based on this, I'm like, I don't really need a frequency analyzer, but since I can analyze frequencies, I can do weird stuff with that. So here's another example that I did in January, where all of this sort of like connects, where you can have like a 3D scene and then make it react to real-time audio that is just hitting the like browser at a given moment in time. So what you're going to be seeing right now is not going to be like pre-programmed, like at this second a light should lit, right? Like should get lit, but it will be just made like in real time by just the sheer like programming of like react to this band of frequencies. So we can play stuff and see what's going to happen. Nothing is happening. Let's see why. Oh, that's because all of this thing that I told you about the sample rate now hit me in the head, since the bands of the frequencies that we are analyzing is not what we wanted. So now external headphones, we actually have to switch it to 48 hertz, which I did, but I cannot show you this on the second screen. It doesn't want me to show you, but I did switch it. So if we reload this, this will work now fine. And I can actually even show you this example before of the waveform visualization that the hair disappeared because I actually checked 48 kilohertz right now. So file chosen, we were post fifth. And after a bit, look, no hair. Like, imagine how long it took me to realize that this is the problem, like 44.1 kilohertz and not 48. But now that we know, I'm not going to make a fool out of myself, and I can actually show you the last example. So this reloaded, and now the actual recognition of frequencies is going to actually work. Hopefully, let's see. Right. So not only do you see that the 3 bars like respond to the melody that is playing, but there's also some like sort of beat. And here I sort of cheated because in the audio workstation that this like music was made in, I realized that like if we actually just keep a sound at a frequency above 20 kilohertz, people can't hear anything there. We can just use this to synchronize tempo to whatever is happening graphically. So we can literally just have like perfectly like synchronized visualizations. And this is important because normally if you just have like a techno song, it's gonna be like 135, it's gonna stay at that tempo the entire time. So that's perfect. But what if you have stuff that's slowing down or like, you know, getting faster in the finale? Like then you have to do some manual like calculations. Not cool. Here, you don't have to, because like this sort of beat at 20 kilohertz that you couldn't hear anyway, because like most speakers don't actually go that far, even if they claim to, that allows me to actually have like both sound and like visuals like in perfect sync. And that's the sort of thing that I like to play with these days. I find it extremely sort of like rewarding to have the visual factor to it, because the most visual thing I've done for Python was adding syntax highlighting to PyRepl for 3.14. But like everything else is really just like this thing, or like, you know, there is now this pointer on thread state, and thanks to this, there's async IO introspection. You should go to the next talk next door, like in BC, like right after mine, to hear about that. But you know, like this gives me an entirely different dimension to working with Python, and the fact that you can do this in the browser now, amazing. So we are essentially done here. And if you remember one thing from this talk, it should be that the same air pressure disturbance can be perceived as a phrase when it's just random and very slow and like, it's, or a beat, or a pitch. It's all about frequency. And that digital audio doesn't have stairs, right? like, okay, so here's our beat and here's our pitch, yeah. But also that you can do all of those things in Python now. You can play with Pyodide, with PyScript and so on. Like all of those examples that I showed you, like were barely like 100 lines or so. And since all of this is open source, it is on PyScript.com, you can already have like examples how to start. So you don't have to like figure out things like I had, like how do you actually pass null to JavaScript? Well, it turns out you don't, so it's a little bit weird. Like none in Python is undefined, but like that's a tangent. That's a rant for me, like for a different time. But now, thank you very much. Thanks for indulging me, and make sure to see Peter's audio talk here yesterday at 5:15 p.m. And if you don't have access to a time machine, you can wait for the recording, and you should, because it is an excellent talk. So yeah, thanks for indulging me. This was Looking at Audio. If there are questions, I can take them. If not, no problem.
Yeah, we have time for maybe one or two questions, and I know Łukasz has said he's got to get to something right away, so if you have later questions, you might be able to bribe him with a beer or something.
I'm here for the rest of the conference too, but now I highly recommend you go to the other room, like for the talk that is about to start in 15 minutes, is it?
I think so, yeah.
Yeah. All right, no questions? Perfect. Thank you very much again.